So. Oh, it is.
No sucks, you know, as a I can start to about. Oh, wait.
They all got responsible needs in. They don't have business needs. It's like.
Oh, wait.
It's sure. Pretty much.
There's it's hard enough to hard enough. I just want to but not saying and you want to create
On the website.
But
You know, that's what they want to take. Have fun.
One more, page 154.
You know. Yeah. Actually. I swear, yeah, I swear.
look at how if they only realized in July. That's true.
All right, good morning, everyone. We're just going to, let me do a quick recap here. When we talk about limits, sorry, we're on page 5 here. When we talk about limits, limit is only going to exist if the graph is approaching the same y value from both sides. So we talked about how visually we can pick 2 points on both sides of the target of wherever we're approaching, and we draw the arrows, and we're asking are the two arrows going to be consistent? Are they both moving towards the same y value? That would indicate whether a limit exists. Now, let's just say we are looking at the behavior of one of the arrows. If that's the case, then we consider that looking for a one-sided limit. A one-sided limit is not a full limit. It is like a partial limit. It is just asking for the movement from one side of that target. So one-sided limit is the y value a function approaches as you approach a given x value from either the left or the right side. And the notation that we're going to see with one-sided limit is going to be a plus or minus kind of in the exponent location for that number. So here, let's say we're approaching 3. Okay. We're trying to see if the limit exists for both sides of 3. So I'm going to pick points on both sides of 3, relatively close. And I'm going to approach 3. One side is headed down towards this point. The other side is headed towards this point. We can already tell the limit is not going to exist because the arrows are not in agreement. But we can find the one-sided limit because a one-sided limit is just the behavior of one of those arrows. So the limit of f as x approaches 3 from the left side. So if we're following the behavior of that arrow, we'll say limit as x approaches 3 from the left side. On the left side, we'll have this negative notation that is in the exponent region, and that is indicating this is just talking about what this arrow is doing. And this arrow is getting closer and closer towards that hole. It's getting closer and closer towards negative y value of -1. Okay. The limit of x as x approaches 3 from the right side of 3, it's following the behavior of this arrow, and this arrow is headed towards a y value of 2. So we say the limit as x approaches 3 from the right side of 3. So 3 plus is talking about what's happening with this arrow, and that is headed towards 2. So are the two sides different? They are. And this is kind of going to be the more formal approach of deciding whether a limit exists. Is the one-sided limits, if they are in agreement, then the limit does exist. But if the one-sided limits are not in agreement, then limit does not exist. So we can say that limit as x approaches 3 of f of x does not exist. And the way that we would write this is we would say the limit as x approaches 3 from the left side of 3 of f of x does not equal to the limit as x approaches 3 from the right side of 3 of f of x. Okay, so this is going to be the formal way of indicating that the limit does not exist because of the one-sided limits not in agreement. So this is the way that we need to be able to write out formally to indicate that the limit doesn't exist. And so this is the way that I need to see you write it. But also these are the ways that I see students write it, which would not be acceptable. So if you say that 2 does not equal to -1, I know what you're doing, but this is not going to be formal enough. So this is not good enough to earn full points if I'm trying to ask you show why the limit doesn't exist. So don't write it this way. Okay. Even though I kind of know what you're trying to do, we're trying to show that the y values are not in agreement, but this is the more formal way. Another way that students want to write it is this: limit as x approaches 3 from the left does not equal to the limit as x approaches 3 from the right. And this is missing f of x, so we have to be able to indicate what function are we talking about. So we have to name the function. So make sure that you leave the f of x in your notation. This is also not correctly written. I know this is the way that we say it, but this is an incomplete statement. We have to indicate, okay, we're talking about the approach, or we're talking about the limit as we approach 3 of a particular function. We have to make sure we name that function. All right, so go ahead and try example 2, A through I, and then I will work through these problems the same time that you guys do. So if you see a negative exponent, that means you're starting to the left of your target, moving towards your target. If you see a plus exponent notation, that means you're starting to the right of your target, and then you're moving towards your target from that point. And if you don't see any positive or negative notations, exponent-wise, that means it's asking for the full limit. It's asking, are the two arrows meeting or heading towards the same y value? If they are, then the limit does exist. Okay, any questions with 2? Example 3 is a bit more challenging because we're going backwards here. We're basically wanting to sketch a graph that satisfies the following conditions. So for part A, order pairs are easy. It's just a single point. If we're asking for limits, then we want to know that the approach is headed towards a specific number. So for part A, g of 3 equals -1. That should be easy. I'm just going to go ahead and plot that order pair. The limit as x approaches 3 is equal to 4. Now, if the limit exists, x approaches 3 as x equals 4, the point doesn't have to live here. So what I like to do is, if ever I'm trying to find a limit, I always like to just have a hole there to begin with, because there may be a statement later on that is going to identify that order pair in a different location. And I think putting a hole there allows us to have more flexibility. We don't have to erase. If we find out that later the point exists at that specific order pair, then we just fill in that hole. So whenever a full limit exists, I like to just have a graph looking something like this, where the graph is headed towards a point, but I like to have a hole at that target point. So as we approach 3, the limit is equal to 4. So that means from both sides of 3, the graph is going to be headed towards 4. So I'm just going to put a hole there, and I'm just going to extend the graph slightly from both sides, because I don't know exactly where the graph is going to extend to, but I do know that the graph is going to have to move towards that order pair. And this is actually going to be the right way to do it, because the order pair is living in a different location, 3, -1. So having that hole there allows us to make sure that we don't conflict with this order pair, because if we put a point there, then it's no longer a function. All right, so I may extend these two lines a little bit later, but I know the graph is at least going to move towards that point because the limit exists. If the limit exists, I have to be able to plot 2 points near that target, and it's got to move towards the same y value. Okay, part C, limit as x approaches -2 from the right side of -2 is equal to 1. So this is only indicating the movement from the right side of -2. So I'm going to find -2, 1. I'm going to put a hole there, and I'm just going to extend the graph starting on the right side, because I know that from the right side of -2, the graph is going to lead me towards that point. Now, this is incomplete here. I'm just trying to meet each of these conditions, and then I can take a look back at what we can do to connect the graphs if we need to. Part D says G is increasing from -2 to 3. So from -2 to 3, the graph is going to be increasing. So I do need to adjust this. This graph does need to be a little bit lower so that it can show increasing. So let me make that adjustment. So now I fulfilled that condition. G is increasing from -2 to 3. Okay, the limit as x approaches -2 from the left side of -2 of g of x is greater than the limit as x approaches -2 from the right side of -2 of g of x. So I do need a graph extending from the other side of -2, but I want it to be higher. So I'm just going to pick an arbitrary point and just have the graph extend from there. You can have it in a different point. I just need this segment to be higher than this segment. Okay, page 6. Okay, if we have a graph, it's easy to see that the value of the limit as x approaches 3. So we want to find the full limit. There's no plus or minus sign, so there has to be an agreement from both sides. We pick points on either side of 3, and we follow our arrows. Our arrows are definitely pointing towards the same y value. They're both headed towards y value of 3. Now, if we have the graph, we can tell what the limit is. But let's say we didn't have the graph. Let's say we only had a table of values. If we had a table of values, we can still make the same conclusion of what the limit is. So for instance, let's say we're trying to find the limit as x approaches 3 from both sides of 3. So I'm going to pick points on both sides of 3. So 2.9 and 3.1 is kind of acting as the starting point of what we did with our arrows. And then we're just following the arrow towards 3, right? We're from 2.9, we're drawing it towards 3. And then from 3.1, we're drawing towards 3 as well. Okay, so both sides are headed towards 3 from both sides of 3. And then we just look at the y values. Are the y values headed towards the same? Are they consistent? So 3.9, 3.99, this is getting closer towards what? 4. 4.1, 4.01, this is also getting closer towards 4. So this is, this one we can say the limit as x approaches 3 of f of x is equal to 4. So this is a table version of finding limits. This is the graphical version of finding limits. But if all the data is here, it should be easy. Now, if these decimals are not, let's say this 3.99 and this is like 6.0001, then you would say the limit doesn't exist, because we do need to see a consistent movement of the y values getting closer towards a specific number. Okay, this next one's a little messy. I'm going to pass this one. We're skip past this one. Okay. All right, the next big topic is finding limits algebraically. So we can find a limit graphically. That's the easiest. So that's why we started with that yesterday. Finding a limit using table of values is easy as well, as assuming, it's a little tedious if you didn't have all those values. But if the table of values are given to you, it should be easy to read. You're just looking at the y values to see if they are headed towards the same number. Now, the last step, this is the one that takes more effort, is finding limits algebraically. So if we didn't have the graph in front of us, if we didn't have the table of values, if we only had the function in front of us, then finding limits algebraically requires a different set of steps. So if you're trying to find a limit algebraically, you don't have the graph in front of you, you don't have the table in front of you. All you have is the function for that function definition for that graph. Then we're going to follow these steps. The first step is direct substitution. Okay, so we always do direct substitution first. That's always the first step. All right. Now, when you do direct substitution for limits, it's more of an information gathering stage. You may not be able to get to the answer just by doing that, but by doing that, you should be able to know what category you're falling under. Okay, so let me talk about what I mean by that. So if I plug -1 in, okay, I'm just plugging in like as if I'm evaluating a function. So I get 1 minus 2 minus 4. That's equal to -5. If direct substitution gets me a real number, then I'm good. I'm done. That's my answer. Okay. There's nothing more that needs to be done. Now, if I don't get a real number, then we have more things we have to do. But let's start with the most baseline, the easiest situation. If my direct substitution works, I can stop. If I have a real number, I'm good to go. Okay, here, number 2, limit as x approaches 2 of 6. I can't plug 2 into 6. That 6 is a constant, so my limit is just going to be equal to 6, and that's a real number, and that's my limit as well. Okay, number 3, we always start with direct substitution first. Okay, even if it feels like you can skip that step, I think direct substitution gives you a foundation for you to make a decision later on. So don't skip this step, even if it feels like, oh, I know what's going on, I'm going to just jump to my next step. Don't skip this step, because it may confuse us if we don't get the result that we're expecting jumping to the next step. So first things first, okay, direct substitution. All right, so we plug 0 in for x. Okay. What do we get? Numerator, we get 0. And denominator, we get 0. Is that a real number? No. Now, this is a very specific here. We call this indeterminate form. And what this is looking like on the graph is it's going to look something like this, where there's going to be some sort of a hole, which means that the point doesn't exist. But if you get a 0 over 0, the limit does exist, because it's only a hole in the graph but the graph is still headed towards the same y value from both sides. So whenever you see a 0 over 0, you can't say that the limit doesn't exist. You just have to do an additional step to get to the answer because something is preventing us from seeing the limit, is blocking our view of the limit, but the limit does exist. So whenever you see 0 over 0, you have to keep going. You know that it's indeterminate form. There's some cleanup steps we have to take to find the limit. We can't see the graph, but we're going to algebraically figure out the graph. So whenever you see a 0 over 0, there is a factor that can cancel. There's something that you can factor out and something that you can cancel out to basically, in a sense, remove the hole and allow the function to see where that point is going to be. So if I look at the numerator here, what can I factor from the numerator? X. So if I factor x out, I'm left with 4x minus 5. And my denominator has an x as well. And this is what's causing the hole to appear. This x over x is causing that 0 over 0 to show up, which is preventing us from seeing what the true limit is. So as soon as we remove the hole, then we should be in the clear. We should be able to figure out where that limit is. Now, this graph is, it's not visually accurate in terms of where that point is. But if I remove the hole and if I try to reevaluate again, I should be able to, this should lead me to a real number here. So if I plug 0 in for x, what do we get? -5. So that is where the limit is, -5. If you were to plot this on a graph, it would show the hole at y value of -5, and the graph will be headed towards -5. Okay. Now, even if it feels like, oh, I know what's going on, I'm just going to factor and reduce, don't skip this step. Okay? If you start skipping this step, yes, sometimes you may save a little bit of time, but there are other situations where it may throw you off. So always do direct substitution first. Again, this may not lead you to the answer, but it will help you categorize which type of problem you're dealing with. All right, number 4. First things first, what do? Substitute, plug -7 in, okay? Even if it looks like, oh, I can factor and cancel out, don't skip that step, okay? So go ahead and plug in -7. So 2 times -7 squared, it's going to be 49 times 2, 98. -7 times 13. -91 minus 7, which is -98. So this ends up canceling out. So we plugged in -7, sorry, and we do get a 0 up in the numerator. And the denominator is also what? 0. So this tells us 0 over 0 in indeterminate form. The limit does exist, but something is blocking our view. All right. So here we can look for trinomial factoring in the hopes of the denominator is kind of giving it away. Okay. Basically, we're looking for an x plus 7 that's hiding in the numerator because we want that to cancel out. And then that will lead us to the limit that we're looking for. Right. So I'm going to factor the numerator here. Okay, so it's very clear. The cause of that 0 over 0 is coming from this x plus 7. So we remove the hole, and then we reevaluate. We do a direct substitution again, but now the direct substitution is just for the reduced expression. Okay, so -7 in for x, we get -14 minus 1, which is -15, and that's our limit. Okay, questions so far? All right, number 5. Limit as x approaches -6 of x squared plus 4x plus 3 all over x plus 6. First things first, what's our first step? Direct substitution. Okay, we don't want to assume anything. Always do direct substitution first. So plug -6 in for x. All right. 36 minus 24 plus 3. Denominator, we get 0. All right. This is not the same thing as this. Okay? If we see 0 over 0, it's indeterminate form. We're kind of there's a bit of a roadblock, but we know what to do to eventually get to our answer. There's an answer waiting for us. It's just not visible at this stage. This is something different. This is completely undefined. So here we would say that the limit does not exist at all. And the reason why is because whenever you see a non-zero over a 0, that means there's a vertical asymptote in the way. At x equals -6. I haven't talked about asymptotes yesterday, so let me just talk about that real quick. So this is what the graph may look like here. So if this was the visual graph in front of you, and I'm asking for the limit as x approaches -6, you would pick points on both sides, and you would draw the arrow. You would follow along the path of the graph. And when you do that, yes, they're both headed towards infinity, but neither of these are real numbers. So if we don't approach the same real number from both sides, then the limit is still under the category of does not exist. So sometimes the graph are headed towards different real numbers. That means limit still means limit doesn't exist. The arrows are not pointing towards the same y value. And then if it's infinity, in a sense, they're both headed towards infinity, but infinity is not a real number. So infinity is also under the category of does not exist. Okay. So the big picture is always do direct substitution first. When you do direct substitution, it's going to instantly tell you which category you're dealing with. Are you dealing with a real number where you can stop? Are you dealing with 0 over 0, which means there's an answer, but keep going because you got to remove the hole? Or can you stop because the limit doesn't exist? And so it's so important that we do direct substitution first. Otherwise, if you're making an assumption, you may guess wrong and then you're stuck because it's hard to know. I think that direct substitution gives us that anchor for us to make that decision later on. Let me do another example here. Let me call this 5b. Okay. Direct substitution first. What do we get? I just created this one for you to copy down. 0 over 9. What would you categorize this as? This one is a real number. This is what? 0. So you would stop and say that is 0. I want to show this to you because I want to show you that just because you see 0, it doesn't mean that it's one category or the other. And these are the 3 variations. If you get a 0 over a non-zero, that is a real number. You stop. That is a true limit. If you get a non-zero over a 0, that is undefined, and there's a vertical asymptote getting in the way. So here you would say the limit doesn't exist. If you get a 0 over 0, the limit does exist. It's indeterminate form. There's a hole getting in the way, and you have to find a way to cancel stuff out. So I want to show you the 3 variations of 0. just because you see 0 doesn't mean it's one or the other. Here are 3 instances where, depending on the location of the 0 and how many zeros there are, it's going to put, categorize you in a different, it's going to put you in a different category. Okay. All right, number 1. This is rationalized fractions with radicals. If you're coming from AB, just want to make a note here, no L'Hopital's rule here. Technically, this is going to be the shortcut that we're going to learn a little bit later on when we talk about derivatives, but we haven't gotten to derivatives yet. So even though technically we can do L'Hopital's rule with this, we're not going to include that in this unit. Okay, so now if you have that knowledge, you can use this to double check your answer, but I'm not going to count it towards credit. If you don't know what I'm talking about, then don't worry about it. We'll get to it when we get into derivatives. All right, first things first. What's our first step? Direct substitution. Okay, so 5n for x. Okay, what do we get? 0 over 0. This tells us what?
Exists.
Yeah, the limit exists. There's a hole. There's something that's preventing us from seeing the limit. Something is blocking the view of our limit. Now, whenever we see a radical involved, we're not able to factor in a traditional sense. We're going to do something a little bit different to try to get this numerator to clean up. The hint is the denominator. You know there's an x minus 5 that's hiding in the numerator, and that's what we want to cancel out. The way we deal with this problem is we're going to rationalize the numerator. You may have talked about last year where you're rationalizing the denominator to get the denominator to clean up. Here, we're going to be rationalizing the numerator in the hopes of getting the numerator to show us a different variation so that the x minus 5 will hopefully pop up. Okay, so this is how we're going to do it. We're going to multiply the numerator and denominator by the conjugate of the numerator. So the conjugate of the numerator, you're going to copy the numerator exactly as is, but you're just going to change that sign between the two terms. So don't change the plus 4, change the minus 3 to a plus 3. If we multiply by the conjugate, the numerator should clean up nicely. And the hope is that an x minus 5 will show up and then we can cancel out. But anything we do to the numerator, we got to make sure we balance it out with the denominator as well. Okay, so the numerator, I'm going to expand out and it should clean up nicely. So I'm going to FOIL this out here. So root x plus 4 times root x plus 4 just gives me what? X plus 4. I'm going to skip the middle terms because the middle radical and the outside radical will cancel each other out. So you don't have to worry about it. That's the nice thing about this conjugate here. And then we're also going to multiply the last two terms here. So this is what? Negative 3 times 3 is minus 9. The denominator, leave alone. Don't try to expand the denominator out because the x minus 5 is already showing what we want to cancel out. If we expand this out into the denominator, it's going to create a whole mess, and we got to factor it out again. So let's just save a step, leave the denominator alone. The x minus 5 is our target. We want that to eventually just cancel out. We know that's what needs to go away. Okay. What does a numerator turn into? maybe you're one step ahead of me here. If I just combine like terms here, what do we get? X minus 5, right? And that's what we want. We want an X minus 5 to show up, and that allows us to see, okay, clearly this is what's causing the hole. We're going to cancel out the expression that's causing the hole. And then that will give us the green light to help us find the limit that we're looking for. So like you said, X minus 5 will cancel out. And there's a leftover 1 up top. And now that we're in the clear, we know that 0 over 0 has been removed. We can now reevaluate the reduced expression, and that should take us to our true limit. Okay? So plug 5 into the remaining expression. Numerator stays as 1. Denominator, we get root 9 plus 3. And so we end up with what? 1 over 6. So if you see 0 over 0, it's going to fall into 3 categories. It's either going to be something that you can just factor out using trinomial factoring or GCF. The second scenario is one where there's radicals involved, and you have to multiply the top and bottom by the conjugate of the numerator in the hopes of finding that common factor to cancel out. And then the last scenario is with complex fractions, where you got to find common denominators and then find ways to cancel and match and cancel out the whole. Okay, so let me go through that example before class ends here. Number 3, we see a complex fraction here, of a fraction within a fraction. But even though we feel like, sometimes you may look at a problem and you feel like, okay, I know where this is going, but show that first step. I need to see that you're checking for 0 over 0 before you commit to all your cleanup steps. All right, so first things first, direct substitution, 0 in for x, what do we get? 0 over 0. Okay. Now, there's a whole mess here. 1 over x minus 4 over x over 1/4 plus 1/4, sorry. We're going to focus on this expression here. Our goal is if we can get that cleaned up to be one fraction, then dividing by a fraction is a lot cleaner because we can multiply by the reciprocal. But right now, these two fractions are separated, and it's hard to clean up that way. So we're going to step to the side here, and we're just going to figure out how can I get these two fractions to merge into one fraction. And to do that, we're going to find a common denominator. So my common denominator is going to include both the 4 and the x minus 4. And then we're going to balance each fraction. Okay, so this old denominator is missing a 4. So I'm going to multiply the top by 4. 1 times 4 is 4. This old denominator is missing the x minus 4. So I'm going to multiply the top by x minus 4. Now that I have a common denominator, I'm going to merge into the same fraction. But realize that this is just going to represent the cleanup of this expression. Now, when you add fractions, you're going to keep the denominator the same. You're just combining like terms for the top. So 4 plus x minus 4 just gives me what? This x. So x. So this is the cleaned up version of what I have here initially. Let me zoom in a bit. So now I'm going to take what I have here, replace the two individual fractions there. And let's see where this leads us. I know this doesn't look like we're making much progress. It still looks a little messy. But the nice thing is that now that we have a single fraction here in the denominator, I can just do keep, change, flip. I can just bring this up to the numerator and just have it at the same stage and see what cancels out. So dividing by this is same thing as multiplying by the reciprocal. So x times. So I'm going to divide by this, which is the same thing as multiplying by the reciprocal of that fraction. So it's going to be 4 times x minus 4 all over x. And now it's more clear because, oh, I can see what's causing the hole. The x over x can be reduced, can be removed. That's what's causing that 0 over 0 to show up. So once I get the x to cancel out, I can now reevaluate my remaining expression, and that should get us down to a real number. So 0 in for x, 0 minus 4 is -4, 4 times -4 is -16. So that's our limit. Okay, I think I pretty much covered all the big things here. So your homework, page 7 through 14. Couple things I forgot to mention yesterday is I don't have a hall pass, so if you need to go to the restroom, you can just go. It's only 10 steps away, so you can go to the restroom, but you don't have to ask me for permission. You can just go. But even if you're going just for like 20 seconds to get water, make sure you close the door behind you. I'm going to just ask the person who's closest to the door just to let you in, but make sure you always close the door if you're entering or exiting the room.
The restroom. I know, sorry. Oh, look, here, like, if I don't have to do something, I'm just gonna draw this in. We're gonna be like, okay, like that, so maybe.
Figure it out. Alright, it should like. It should be good at digital. I don't know, all people, it's live for type of English. No, that's how you see it. I woke up at the I need to read the book. So you go through that. And like on some days.